Alright, class. Welcome to the class today. We are going to talk about the Exergy chapter 8. Exergy. Exergy, it's pretty uncommon term. Some of you may already heard about it, some of you may not. So Exergy is also, in thermodynamics we use Exergy to determine the quality of the work or the possibility of conversion of energy to produce the work. So we will talk about the Exergy in this chapter. We'll talk about, for today's class, we'll define the Exergy, and we'll discuss about the the factors that are affecting the Exergy, or the process that contributing in Exergy. So Exergy, let's consider that you have a coal mine or geothermal oil, right? So if you have a geothermal oil, in this from this geothermal oil, it has abundant amount of energy, right? So now if you want to use that energy as in a power plant, right? If you have a power generation, if you have a power plant, and that energy you are basically using in this power plant. Now the question is that how rich is this energy, right? How rich is this energy? That means that if you extract energy from this one, that 100% is converting to this, or 100% energy is useful in the power plant to produce the electrical energy, or 50% of this energy is being used and 50% is waste. So to determine the quality, we have to have some sort of term, right? So if we see that chances is that only 50% energy from this geothermal oil we can use or utilize in the power plant, then it's going to be very expensive, right? And it's not going to be efficient energy source. However, if we see that anything close to 100%, then this is a really rich energy system. So in that case, the cost of this entire system or the power plant or the production of the energy will be reduced, and it will attract, right, a lot of energy producing companies that with low cost they're producing high quality of energy. So now in this scenario, Exergy plays a role. So Exergy is basically defining, or in this scenario we are basically looking for availability of energy, right? We are looking for availability of energy. So if we want to define this term, then we can define the Exergy. Exergy is nothing but availability of energy. So as we proceed further, we'll define more, or we'll give like more specific definition of the Exergy, but just keep in mind that availability of energy is also known as the Exergy. So how we can produce, or the available energy, how we can convert it into the work. So basically work depends on three things, or work is a function of the process, first of all, right? Whether it's a reversible process or whether it's a irreversible process, then process path, right? And then initial state and final state, right? So work depend on this thing. Why? Let me show you. So if it is a PV diagram, so for example this is P and this is V, then if you have this is state 1 and state 2, let's define 1 and 2, then work is depending on these two state and the process path as well. So for example, first thing, so the first process path is like this, and then second process path is like this, and then um, third process path is, let's say the third process path is this. So then the area under this each of this curve is different. That means that, whenever it's taking this process, then area under the curve is maximum. Whenever it's taking this process, this area under the curve, of this curve, it's relatively smaller than this one, right? So that means that work depend on the process path. Also work is depending on the initial point and the final point. So now the question is that work is depending on these three things, then what are the things, for in Exergy, right? What are the things depending on or Exergy, what are the things, it's the parameter, right, in case of Exergy. So let's take a look on in the case of the Exergy. So before defining the Exergy, let me give you one more example. All right. So basically, there is a term. It's called the dead state. Dead state. In equilibrium state, we see that there is no. For example, if a system is thermal equilibrium, there is no temperature difference, right, within the system. So then we can conclude that, okay, this is the thermal equilibrium. However, for dead state, if you have a system, for example, if you have a system, that system has let's say it consists of air, right, and it has 25 degrees C, it has 100 kilopascal pressure, and then it doesn't have any velocity, and it doesn't have any elevation, right? So, and it's in the floor. Now the thing is, environment temperature or ambient temperature is also 25 degrees C, and also the pressure is 100 kilopascal, right? 100 kilopascal. So if there is no velocity and you have no elevation change, and both of the, and this entire system is, it's basically in equilibrium with the environment, then we can conclude that this system is a dead state condition, right? So a system is said to be, or is said to be in dead state when it is in thermodynamic equilibrium. When it is in thermodynamic equilibrium with the environment. Right? So that's the definition of the dead state. So if a system is thermodynamic equilibrium with the environment, then it's said to be the dead state. Also keep in mind that in dead state there is no velocity or elevation change. That means basically no kinetic energy and no potential energy. So also no kinetic energy and potential energy. So this is important to know as well. So now one more thing, when we define the work in previous chapters, we also defined some basic thermodynamic definition. For example, system, surroundings, right? So if you have a system, for example, this is a high temperature system, right? So, and then if you have, like, we define the surroundings is outside of the system, right? Basically we defined previously the system with the imaginary boundary. However, we are putting that imaginary boundary bit outside of the system. So for example, if this is the 70 degrees C, then at immediately or very close to that system, we'll see maybe 50 to 60 degrees Celsius, and outside, like far from that system, we'll see that this temperature is 25 degrees C. So the immediate or very close to that system, we'll see that higher, relatively higher temperature, right? So in that case, if we see that there is a temperature existing, high temperature existing in between this, the environment condition and this condition, like the system temperature, right? So there is a difference between this 2 point, right? So this is 70 degree and this is 25 degree, and in between there are also some temperature. So in, if that's the case, then we call its immediate surrounding. Immediate surroundings, we call this one as the environment. Excuse me. And this one is system, right? Just to give you the definition, so one more thing we added in the Exergy chapter is the immediate surroundings, right? So the distinction between the surroundings and immediate surroundings, I already mentioned that there is a temperature difference in very close to the system, then we if there is any temperature difference exists between the environment and the system, then the imaginary boundary or imaginary area, we can consider that the immediate surrounding. So we talked about surroundings, immediate surroundings, right? Immediate surroundings, system, dead state, right? What else? Environment. So these are the things basically we need for to define the exergy. So basically we will talk about the the exergy, or what is the how we can get the maximum amount of, like, for in this case, like I just gave you the example that if you have an energy reservoir, from that energy reservoir, how can we maximize the work, or what are the key factors that can help us to achieve the 100% of work, 100% conversion of the work, or close to 100%, right? So those are the things we will look for in this chapter. So if a system is reversible, right? So a system delivers the maximum possible amount of work. Maximum possible amount of work as it undergoes a reversible process. Now if I ask you that what if there is an irreversibility, so if there is an irreversibility, that means there is some loss as well, and we saw in entropy chapter, right? So if a system undergoes a reversible process, then there is no entropy generation, but if the system undergoes a irreversible process, that means that if there is an irreversibility, then entropy always generated, and also there is some loss. So in this case, similarly, if it is a reversible process, then it will produce maximum amount of work. If it is a irreversible process, then it will have some loss. So a system delivers the maximum possible amount of work as it undergoes a reversible process from the specified initial to the state of its environment, or dead state, from the initial to a dead state, right? So this is very important. So this thing, the conversion of the maximum energy it's depending on the reversibility or irreversibility of the process. So this represents the use of like the full potential of the system, right? So that means that, excuse me. So this is basically defining this, the exergy. How? So the useful work potential. Excuse me. Useful work potential of the system at the specified state is called exergy. So two things I would like to emphasize. One is that I'm keep talking about the specified, right? So here, and also I mentioned is that reversible from initial to, so specified state, that means that it has to be from initial state to a dead state, right? If it doesn't go to the dead state, that means that we cannot convert to the maximum amount of work. That means that if, and a system will not gonna reach to the dead state, right? A system will not reach to a dead state if there is any irreversibilities. If there is an irreversibility, it will not gonna reach to the dead state. In that case, we will not gonna get the maximum potential of work from that system, right? So that's the thing, keep in mind. So exergy is highly depending on the whether the process is reversible or irreversible, whether the process can reach to the dead state, or there is, due to the irreversibilities, that process cannot be reached to the reach to the dead states. Then it's highly depending on the state. So that's the definition of the exergy. So now let's go ahead and start do the we'll do some problem, but I would like to define couple more definition, or couple more the parameters for the exergy. So first thing is that number one, exergy or work potential exergy or work potential associated with kinetic energy. So exergy for kinetic energy, exergy of kinetic energy equals to, we will define it xke, excuse me, xke equals to v square divided by 2. And then number 2, exergy or work potential associated with potential energy, PE, right? So exergy of PE, which is xpe equals to z, right? So if we have any elevation of a system or energy system, then we'll determine the exergy of that system by using this formula. So we'll go ahead and do some problem based on this two energy, kinetic energy and potential energy, and then you will see that how basically we are determining the availability of the energy being converted in work from a thermodynamic system. So we'll go ahead and do that. So let's just move to the one more topic, reversible reversible work and irreversibility, right? So topic 8.2, reversible work and irreversibility. So this is topic 8.2. So in the previous classes we saw that if a system is a closed system, for example, right, if this system is a closed system, then we saw that, let's say, and this can be changed, right? So this is state 1, for example, and it's coming to this state. This is state 2, and this is a closed system. And we also saw that if we have a steady flow device, let's say this is a compressor, right? Steady flow device, compressor. Here also this is state 1 and state 2, right? So the P1, P2, we can see that P1 is less than P2 here, and similarly here P1 is less than P2, right? The difference between these two is that this is a steady flow and open system, steady and open, right? However, this is a closed, right? So for this closed system, we determine the work done by the system, right? Work done or work of that system, we define that P dV, right? Change in the volume. If we give the pressure constant and change the volume, we saw that actually, let me write this one. So we are changing the volume, right? So this is V1 and V2, and in this case we are changing the pressure, and we can see that V1 is greater than V2. So in this case, closed system, we determine the work done by the system or work consumed by that system is equals to P dV. However, if it is a steady flow device, W work equals to, we determine that it's V dP, right? So we saw this two difference. Now, what if there is a reversible? What is the reversible work and irreversible work? So let's go ahead and define those. So if for in the exergy, we basically are looking for the availability of the energy, right? So that means that we want to make it reversible. And if there is any irreversibility, that means that it's not gonna utilize the 100% of that energy. So that means that basically we are destroying or wasting the energy, right? Which we can term as energy destruction. So if it is a reversible, then full potential to convert into work, right? However, if it is irreversible, then it's a destruction of energy, right? So irreversibility is not desired for a system. So now if we look at the work, then reversible work for a system, then we can define the work of surroundings equals to basically P0 times V2 minus V1, right? So in this case, like for the closed system, if we have this system. Now the difference between the actual work and the surrounding work, it's called the useful work, right? So why I use the surrounding work? Surrounding work, I'm basically using, to define this, or to distinguish between this reversible work and irreversible work. So basically, I'm defining in the surrounding work, which is the work done by or against the surrounding during a process, right? Work done by or against during a process. uh, Actually, work done by or against the surroundings, against the during a process. So now the useful work, which is basically the exergy, right? Or so the useful work, useful, let me define it like this way. W useful, right? Useful work, it's basically the work, total work minus work surroundings, right? So which is nothing but W surrounding. We just saw that P naught equals to V2 minus V1. So the difference between the actual work and the surrounding work is basically the useful work. If I ask you that what is the useful work, then you will say that the actual work minus surrounding work is known as the useful work. Now this is the important thing, right? So case 1, reversible work, what will gonna happen? So if it is a reversible work, then we can define the reversible work equals to W reversible, which is the maximum amount of useful work, right? It is possible to produce maximum amount of work, right, as a system undergoes a process between specified initial and final state. Specified final state, right? So in that case, if the process is reversible, chances is that we can convert all of those work in if the process is reversible, then chances is that all of the energy we can utilize or convert in the work, right? However, if it is a irreversibility, or if there is an irreversibility in the process, then how we can determine that irreversibility, right? So irreversibility, we can express it as I. Irreversibility we can determine by that the reversible work, which is basically ideal work or the maximum amount of work, right? W reversible minus, if we subtract from that work the useful work, right? W useful, then we can get the irreversibility of that system, right? So either we can express them as the output, or we can express them as a input, right? Reversibility input minus W useful of input, right? Either way we can determine the irreversibility of that system. So basically there is a sign convention. If it is a work producing device, I'm pretty sure you guys know which are work producing device and which are work consuming device, right? If it is a work producing device, then reversibility of that system or reversible work of that system is greater than or equals to the useful work, right? However, if it is a work consuming device, work consuming device, then we'll see that W reversible is less than or equals to W useful, right? So that's the important relationship between the reversibility and irreversibility. So I think that's all for these two topic, 8.1 and 8.2. We'll go ahead and solve the math problem based on these two topic and see that how much energy we can, how we can maximize the energy to produce the work from a thermodynamic system. So that's all about the